Alan and Helena. They're going to talk about from zero to cloud, the easy way. All yours.
Hola, hola. Vale, now. First of all, as Jordi said, it's super nice to have so many familiar and friendly faces around, so thank you all for organizing. Okay, wake up question. So how many of you ever had to install the same software on different machines? Raise hands, don't be shy. I know it's early, okay. So it's quite a bit of a pain, right? Because you have to compile everything again, and if it's different architectures, so you will have compilation problems, and then you will have to send a request to the support team. So what if I told you that the European Environment for Scientific Software Installations, EESSI for short, can help you with that? Well, today he is Alan, I am Helena, and we are going to show you, with other things, how to go from zero to cloud the easy way. So first of all, why are we doing this? Well, sure you know that the scientific software environment is already like huge with all this AI boom, all the bioinfo packages, all the engineering, physics, blah, 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 and it just keeps growing. And to top everything, scientists usually have to run their codes on different machines. Sure, you have like cloud instances to have more flexibility, but it's true that the HPC clusters are usually quite heterogeneous architecture-wise with all these Intel, AMD, ARM, and I really hope to say in some years RISC-V clusters too. So, and I can assure you that from a bunch of user supports and sysadmins in the room, we always fall short to supply these scientific software installations. So, what we want to do with EESSI is to provide a truly uniform software stack, and that means that every machine where you have EESSI available, you will find the same software. And everywhere, it's everywhere. It can be your laptop, it can be an HPC cluster, it can be a Raspberry Pi, or it could be a cloud instance, as we are going to show you today. And it's very, very important to point that this software is optimized for the machine it will run, because we are doing high performance computing. So with this, what we are avoiding, so we are helping to avoid duplicate work among user support and sysadmins in the world, because we are all together in this. So you sure have heard of tools like EasyBuild or SPAC. Well, with these community projects, we are helping. So we are sharing recipes or steps to build some software, but with this, it's like a step further. We are all building together a distributed software stack. So it's like a complete rethink on how we share software. And with tools like this, we also facilitate HPC training and development of codes, but that's for another chapter. If you're interested, you can ask us. So as it usually happens with things that sound too good to be true, it's true and it works. And the way we make it work is with this layer implementation. But before we get into that, some key points is that, remember, all binaries are streamed, and EESSI is built to be independent of the machine it will run, so it works everywhere. And we have these libraries that detect the architecture underneath, and they compile accordingly, so everything is optimized, because again, we do high, now you say, performance computing. Okay, we need to wake up a bit more. So the so-called layers, I'm going to run through it very fast because we don't have the time, but again, if you're curious to know how it works, Alan and me will be very happy to solve your questions. So underneath of everything, this is not easy, this is the machine, we have our iron with whatever architecture it has, and it has installed its host operating system. Again, it can be anything. And this host operating system usually provides the drivers for network, GPUs, and stuff like the scheduler or the resource manager in question. And then on top of it, then it's where EESSI starts. We have the file system layer. This is like the infrastructure for distributing and streaming the binaries and the libraries. And this is done through Slurm BMFS, which luckily enough, the next talk is all about that. So I leave the privilege to explaining it to the next speaker. And then sandwiched in the middle, we have the compatibility layer. You probably heard about Gen 2. Technically, it's an operating system too, but what we are doing here is that we are like installing it in a particular prefix, so it's a container without being a container. And this way, we can compile all the applications in the software layer on top of it to point to there. So we don't have glibc problems and that kind of stuff that it's not nice to have. And in this software layer, on top of everything, we have EasyBuild and Elmod to help us compile, generate, and expose the module files, and ArcSpec, which is the library that detects everything underneath. So this being said, I'm not going to get too technical, but it's nice to know that all the binaries and libraries are hosted in European servers, in this case in the Netherlands, and we have mirrors everywhere, well, everywhere, so in Europe and some in the US. Another nice thing to know is that one of the major goals of EESSI is to be available in the major Euro HPC systems. So if you're a researcher and you need to run your code somewhere because you got an hour allocation, you will find the same software everywhere and you won't have to go through the burden of compiling everything by yourself or having to request it. And we're doing a good job so far because EESSI is already available in Deucalion, Vega, and Carolina natively. In Mare Nostrum 5, it's a different setup, but it's definitely there. And it will be in the first exascale system of Europe. The job is, the work is done, we just need the machine to be in production. And if you want to check other machines where it's available, you have a nice list online. And another nice thing to mention is that, yeah, EESSI is funded mostly through the multi-scale COE, but it's an open source thing, and you can contribute to it in case you're missing some software installation. So don't be shy, because we are about to reach like 1,000 software installations. And we have some scientific software superstars like Espresso, LAMPS, GROMACS, WRF, and a lot more. You can also check what is available in the link there. And another super nice thing, last year we won the HPC Wire Reader's Choice Award for Best HPC Programming Tool or Technology. So, quite nice too. And now I shut up and I leave the floor to Alan to give his super long demo.
I don't know if it's going to be so long. Yeah, it's my job to take a few risks. So I'm going to do a live demo, and hopefully the network will let me do that. So we wanted to show off like cloud environments. So to do that, I just want to show you like the most basic thing that you can do, which is like to bring up an instance and make EESSI available there. I'm using AWS here because I'm pretty familiar with AWS, but I also use Azure as well, right? So so I'm going to start by choosing an unusual operating system. So I'm going to take Amazon Linux, their 2023 image. To change things up a little bit, I'm going to choose an ARM instance type. I'm going to take a few CPUs because I want to actually run some code. It's a little bit slow. I'm hoping that'll be okay. So we'll take C6G to X large. So that's 8 CPUs. That's an 8 CPU instance. And then I need to give it a key pair so I can actually log into the machine. And that's basically all I need, right? So I've just chosen my instance size and what image I want on there, and then I need to give a key so that I can actually get into it. And then once that's done, I can launch my instance. And of course, the Amazon images are extremely quick, so by the time I actually get to copy the login command, it'll probably be up and running. So I can connect to the instance. And we're going to use SSH. Let's see, SSH, here we go. And the command is down here on the page, so I can copy that over. So I'm going to paste that into my terminal. Hopefully you can see that terminal okay here. I've made the text reasonably large, at least. So it has never seen that host before. So we're in, right? So we're now inside this Amazon image. There's nothing here, not even Git, right? So nothing is installed just yet. So sudo, I actually need Git because I want to show you an example. Sudo yum -y install Git. And that shouldn't take too long. While I'm letting that do its work, so I'm going to use a demonstration repository that we have. So we have the EESSI organization on GitHub. Everything we do is open source and it's available there. So we have a demonstration repository. I'm going to clone that over. So I need HTTPS to do that. So I'll copy the repository. Okay, so Git is installed. And now I can git clone the repository. Inside here, if we go inside, we can have a little look around. We can see we've got different application codes. Maybe the blue is hard to see in the screen, but we've got things like Bioconductor, Espresso, Gromax, Nextflow, OpenFOAM, PyTorch, Quantum Espresso, like some pretty big applications are in there already. And there's a scripts directory as well. So if I go into the scripts directory, there's a few things in here. One of them is to run EESSI inside a container. We're not going to do that. I won't have time to do an example of everything. So I'll do the basic one where we install EESSI. So we can run that script already. But the way the script is set up, by default, it will just tell you what it would do if it had permissions, right? So it requires sudo because it's going to install packages. But you can look at the commands that would actually run. So what it's doing here is installing a few RPM packages. The setup for Amazon Linux is a little bit different to the other operating systems because for RHEL systems and Debian systems, you have a repository that you can just install. But in the case of, at least in the past, in the case of Amazon Linux, we had to install the RPMs directly. And then it just sets up some settings in a configuration file. So basically, it's telling it how to connect to the EESSI infrastructure. So that's a direct connection for now. You'll understand maybe with the next talk why you might have different settings here. And then there's a quota limit as well. So what happens is on the local system, you assign a certain amount of space to the software stack. And you say you can use up to, in this case, 10 gigabytes to store the software. And basically, it's a first in, first out the cache. So it's like a caching system for that. So if you use a particular set of software, that software will be available and always be available. But if you use a lot of software, then maybe things will be moved out of the cache. But that all happens. You don't know when that's happening, basically. So we can run that script then with the sudo in front, and then it will actually run all the commands. This takes about a minute. It's a few packages, and it's only a couple of packages, but they have quite a few dependencies. Things like AutoFS, right? So we're using AutoFS to mount this remote file system. So that shouldn't take too long, maybe a minute or so. And so basically, what's happening now is it's just installing those few packages, it's configuring a few things, and then we install the EESSI configuration file for CVMFS, so for our particular repositories that we ship. And now we have a new location on the file system. So if you look under /CVMFS, it seems like it's empty. So we have this new location, CVMFS, but it seems to be empty at the moment. That's because the locations underneath are AutoFS mounted. So if I actually know what I'm looking for, so in this case, software.easy.io, if I do an ls on that directory, it takes a second the first time, but it will auto-mount that location, and all of the files all of a sudden are available here. So now I can initialize the EESSI environment. What that means is I need to detect what hardware I'm actually on, and based on that hardware, it will use a particular Gen 2 prefix layer, so one that's compatible with my system, for the family of CPU architecture. And then for the scientific software, it will use a specific stack that's optimized for the hardware that I'm actually on. Right, so we can do that. We can source the script. I, of course, know this all off by heart, but if this is all in the documentation, how you do this. So we will have different versions of EESSI right now. We only have one, 2023-06. The software is a lot more modern than that, but that's when we built the Gen 2 prefix layer. We will have a new release of EESSI in the next couple of weeks. And then underneath here, there's an initialization directory. I'm going to use the lmod initialization because that gives me different shells. There's a basic bash initialization, but the lmod initialization allows me to use different shells. So maybe I have a different shell, but I actually do use bash, so I do want the bash initialization. So I source that directory. Again, it's taking a second because it's talking to the remote file system and caching the files locally. It tells me that's available now, so I can do module avail. And see, I have lots and lots and lots of software now available on the system, okay? So now I can go back and I have these demonstrations, so I can choose one of these to run. So let's do the Nextflow one for now. So I don't know if there's any bioinformatics people here, but you've probably heard of Nextflow. So we have a couple of scripts in here. The run, we don't really care about what Nextflow is actually doing, but there's a run.sh script which basically just loads the modules that are required to run the example, and then it just runs the Nextflow script. So we can run that already. So let's try that, see what happens. And again, it's talking to CVMFS to download the files that it actually needs to run this workflow. but that's it. It's already running, right? So we're already, Nextflow is already available on the system, and it's running the workflow, right? So we're immediately able to do work. Okay, so that one ran in 14 seconds, right? So we had the entire workflow going. We didn't actually install Nextflow. It got pulled in automatically. The files that were needed to actually run that workflow were pulled in automatically by CVMFS. So we could do another example, again, just to show you. So we could pick like Gromax, for example. Same setup here. There's a run.sh script, which like downloads some data that's needed to run the example and then runs that example. So we can run that script as well. And you can see that, like in some cases, depending on how close you are to the infrastructure, it moves really quickly, right? So you wouldn't even necessarily notice that you're actually pulling in files from a remote system. So Gromax is already running now and running that particular example. I think this one takes maybe about a minute. So I'm not going to wait for that to happen. So I wanted to show you a second example as well. So I'm going to launch another instance. I want to launch a new instance. And this time around, I want to show you the GPU, our GPU integration as well. So this one is a little bit gamed because I need GPU drivers on the system in this case. So I've already installed. So I'm going to use my own image that's been a little bit pre-prepared because I needed those GPU drivers installed. So this time around, I'm going to use my own AMIs, and then we have one that's specific here for the workshop. So it's a little bit clunky responding, but let's see if we can get this. There, oh, there it is. Right. So there's my image. This one with the GPU. So it already has EESSI installed, and it also has the GPU drivers installed as well. For the instance type, For the instance type, we obviously need a GPU. So we're going to use a G4DN. And I'm going to be cheapskate and use a pretty small instance here, 2x large. I get a GPU with 2x large. Again, it's just 8 CPUs, but it has a GPU attached as well. This is a T4, I think, so that'd be compute capability 7.5. I can use my SSH key again to be able to log into the system. This one takes a little bit longer to boot because it's a Rocky instance, so it's not as quick as the other ones. It takes about like 30 seconds or so to actually boot up. I will take the SSH command because I need to know what the IP address of this thing is. And yeah, okay. So there's my SSH command. Just to show you here, the Gromax example has already run, right? So that worked. Kind of performance is roughly what I've seen in the past, right? About 5 nanoseconds per day simulation. And the CPU usage is about 800%, which is just what I have, 8 CPUs, right? 8 OpenMPI threads, or OpenMP threads. So we can exit out of this system now and then log on to the other one. There's a slight, because it's a Rocky instance, I know I need to log in as Rocky here. So let's see if that's already available. Not yet, it's still booting. So yeah, last night when I was testing this out, it takes about like 30 seconds to a minute for this to boot. So again, yeah, this instance is a Rocky instance. It's actually Rocky 8 because I did this image a while ago. And it just has the GPU drivers installed, and it has run that script already to install CVMFS as well. And here we go. That's available now. Okay, so we're logged onto this system. Let me just clear the screen. So we're logged onto the system. We can see /CVMFS is already there. It seems empty because I haven't actually mounted the repository yet. So now we can see if we do software.easy.io, things will appear. It'll take us, it's a different machine, so it has to recache everything. Everything is available again. I can source my source /CVMFS, software.easy.io, and then the versions. Again, all of this is in the documentation. I know I'm moving very, very quickly here. And bash, right? So again, I can look at the available when this works. Again, it's pulling in these files, so it takes a second for it to talk to our infrastructure to get the files. When that works, I see lots of software, again, is available the same as before. But I want to see the GPU packages, and they're not actually available yet here. So it's taking a second, but when the command comes up, we'll see that the GPU packages are not available here. And that's because we haven't told the compatibility layer that the GPU drivers actually exist on the system. So we need to run a particular script that allows the compatibility layer to be aware of the drivers that are available on the system. So let's run that script right now. I've also set up the permissions on a certain directory in a certain location so that I can run the script and make symlinks to the drivers that are on the system. So cvmfs software.easy.io, we want versions 2023-06, and then there is a scripts directory in here, GPU support, NVIDIA, and then we have a few things, but the one that I'm interested in is to link the NVIDIA host libraries. So I can run that command. And then it's finding the drivers that are available on the host system, and it's linking them to a very specific location so that our compatibility layer knows that they now exist. Now, that hasn't changed my view of the software just yet, because I still don't see the GPU software just yet. What I need to do, the way CUDA compute capabilities work, the major version of the compute capabilities, that device code can run on anything in that family. So 7.0 code can run on 7.5. That's perfectly fine, right? So you can always have JIT compilation of the GPU stuff if that's available in the executable. But in our case, we don't necessarily have that, right? So we need something that will run on the device code. So the way we deal with that in EESSI is we always make the major version available, so 7.0, that's our approach right now. And that will always work on 7.5 as well. Am I out of time? Well, anyway, I'll do this very quickly, right? So because it's 7.5, I need to point it to a very particular EESSI accelerator target override equals and a location as well. This is all in the documentation, NVIDIA/CC70. And then I can reload a module, the EESSI module avail. Now we see this CUDA code is available at the top here. I can load CUDA samples, module load CUDA samples, and then I can run a device query, which is available from the CUDA samples. And it successfully sees my GPU. I'm going to stop there. I wanted to show you some other stuff so this is the basis of things that you can offer in the cloud space. So we also are able to bring up a cluster that supports EESSI with a tool called Magic Castle that works across various different cloud providers, so AWS, Azure, Alibaba, OpenStack, all these types of systems as well. So you can have a cluster that has this software stack available. And then we have something special for parallel cluster as well, so where we're able to inject the MPI that comes from AWS as well. Sorry for taking a while.
Some questions? Yes, coming.
Hello, Alan. Thank you very much. How do you extend the software stack if, based on the defaults, but you want to add some things that are not in the original?
So we have a special module for that. So there's and this is also documented as well in the documentation. So there's a module called EESSI Extend. So if you're familiar with EESSI Build, all this module basically does. What did module load? Sorry. All this module does is set up some N52 grep EESSI Build, right? Grep. All that does is set up a lot of variables for EESSI Builds to configure EESSI Build to be aware of where things are, and there's a sys prefix involved, right? So that you're talking to a different operating system, and EESSI Build itself is aware of what to do in that scenario. And so to build on top is basically, if you have the EESSI config, the recipe, at least the intention is that you would just load that module and then run your recipe. As long as the tool chains that you're trying to use are available in that system, it will just build on top of what's available there. Hi. And we use that ourselves. That's actually how we add software. So it should be a reasonably smooth experience.
Hi. Is it possible to have clone the rep of the software locally? or do you have always to have the connection to access this easy repository of the software available?
So just if you go through the step that I did, right? So running a script like that is going to install some packages, which is CVMFS. You mean make a whole copy of the entire stack? Because you don't need to do that, right? That wouldn't necessarily be a good reason to do that. If you wanted for like security or like to make sure that you always have access, there's another way of doing that, and that'll probably be explained in the CVMFS talk to maybe make that clear.
Okay,
You can do it. I mean, it's just a location in a file system. So you could copy everything that's inside. It's a POSIX file system. You could copy everything that's inside. As long as you mount it back to the same exact location, things will work just fine. But you wouldn't necessarily want to do that because CVMFS has deduplication. And even with deduplication, we're talking about, right now for our stack is something like 200 or 300 gigabytes, right? That's deduplicated. So if you expand that size, that's probably going to be like significantly larger. And there's no real reason to do it, to be a different approach if you really wanted to provide that.
Okay, so we are going to move to the next speaker. Thank you so much, Alan.